So we are now here. I am just writing the steps. Plot yield strength and fracture stress as functions of temperature, right? You have the values minus 100, 0, 100, 200, 300 at different temperatures. So at these points, you have the values of K1C and you have the values of sigma ys, yield strength. So just write a very rough graph on which the temperature is minus 100, 0, 100 and so on, and plot the values. So you will have two graphs. Assumptions, very critical. Write the assumptions that we have to assume that this is a plane stress case, because you know that the equations have been derived for a plane stress condition. Plane strain is different. And you assume y is equal to 1. So these two are the assumptions. Now variation in fracture toughness is linear, right? K1C is like this. So this with respect to, right, this with respect to sigma is linear, not with respect to A. That is there already, it is there. So it is linear. So you can take only the two endpoints, only at one endpoint and only at the other endpoint. You don't need to draw all the points, right? So this is a trick. You will otherwise have to calculate it at minus 100, 0, 100, 200, 300, 400. But if you just do at minus 100 and 400 the end temperature, then that is it, right? So for example, we are saying that at minus 70, for example, at minus 70, this value is 56 megapascal, right? And so on. So fracture stress is 258 at minus 70, 458 and so on. Maybe I have written something wrong. Just recheck the value. Plot the line. Now design criterion is leak before break. Leak before break, right? So this is very important. The critical crack size at fracture will be given by the wall thickness of the vessel, right? That 2A is equal to 2T or A is equal to T, right? That you have an edge crack at the end inside wall, and when it starts to grow, then it grows, and as soon as it goes through the complete thickness. I was just telling you, right, that it is leak before break, so the size of the crack will be equal to the thickness. So now on the next page, I have shown you the plot, and you will see that the intersection point is roughly at about 221 Celsius, right? So your conclusion is that fracture is more likely at temperatures below this point, and yield is more likely above it. So this is your solution. Let us go to what I have done for you. Right. So on this size we have the critical stress in megapascal. On this side is the temperature. Remember, from minus 100 to 400. So right, this blue line is the fracture stress, and this red line is the yield stress. So this, we told you that because this is linear behavior. So you want to find only at one point and only at the other point, and this will be a strain line. But for the yield stress, remember, right, the equation is given in the question already. So at minus 100, find the value at 0, find the value at 100, find the value at 200, at 300, at 400, and this graph is roughly like this, right? This graph is roughly like this. So I have tried to divide from 100 to 200 into equal intervals and so on. That is why we can say that this is roughly this value and so forth. But even if you are, off by 10, 15 numbers, then it is roughly okay, right? So that is why we stressed in the solution in the question that do it graphically. So you plot these two lines and you have a rough answer. Let's go to the last question of the midterm exam. It is sort of from the book exactly. A flat plate made from a brittle material contains a macroscopic through thickness crack with half length A1 and notch tip radius rho. A sharp penny shaped micro crack with radius A2 is located near the tip of the larger flaw. The figure is given. Estimate the minimum size of the micro crack required to cause failure in the plate when Griffith equation is satisfied by the global stress and crack size. We even solved this exactly as an example during the class. So you see, you guys always I mean, some of you say, please give us easy questions. Some of you ask me what type of questions there will be. My answer always is, not in this course, in every course, that the way I generally would try to design my quizzes and midterms and finals would be that there should be, say, roughly one question out of 3 or 4, which is rather very easy, which is sort of a bonus for everybody. There are 1 or 2 questions which are medium average grade, that people who are of average intelligence and who do average preparation should solve them. And there should be 1.5 question which is a little more challenging, so that people who have really worked very hard in the course should get an advantage compared to everybody else. So this question is an exact solution of an example in the class, right? So all these steps are there. It's just that in the book they have written only 1 or 2 steps. You are required to write all the possible steps. So I have already shown you, because the Griffith equation is there and the equation is given on the diagram also, right? So sigma f is equal to 2 e gamma s pi a1 under root. This is from the Griffith side, right? Sigma a is equal to 2 sigma f root a1 by rho. This is given on the diagram. Sigma f is equal to pi e gamma s 2 upon 1 minus nu squared a2 under root. This is for penny shaped crack, right? So you start combining, that you have 2 e gamma s this that. So you have the equation instead of one type of sigma, right? Where is the sigma? This is the sigma. So you have 2 sigma f. So you combine them, you combine this equation, right? Just go ahead and look, and then from both sides you start deleting common terms and so on. So 2 into, right, this is, if you square both sides to remove the square root signs, then this will be 4, this will be 2, this will be pi, right, this will be 1 by delta, all the others will cancel out, and so on, right? So this is the equation. Then from the left hand side square it, from the right hand side square it, cancel all the e gamma s, right, and so on, and you will have these values. So from here then a2 is equal to pi squared sigma upon 16 1 minus nu square, right? So this is the radius of that penny shaped and so on. So again, right, if this was a brand new question, this will take some thinking, but even then the book is open. The book is open, right? The Anderson book is there. You exactly know the chapter. If you are well prepared, you know exactly where are the equations to handle this particular one. This is chapter 1 or chapter 2 or chapter 3 or chapter 5, and you just apply yourself and do it, right? So that was the end of the midterm problems, and we are now going to quiz 3. And once again, question 1 will be the multiple choice. This time I think you are in EPFM or something like that. Surface energy per unit area is equal to dash of fracture energy, 1/2, 1/3, 1/4, 2/3. So the obvious answer is 1/2. You remember that the surface energy gamma s given, as soon as a crack is there, there is the upper side of the crack and the lower side of the crack. The 2 surfaces are created, right? So the surface energy is 1/2 of the value given. Experimental fracture strength of brittle materials is dash orders of magnitude lower than their theoretical cohesive strength, 3 to 4, 1 to 2, 2 to 3, 4 to 5. So remember that there is a factor of roughly 1 upon pi. Pi is 3.14, right? So the correct answer is 3 to 4 times. 3 to 4 times. Again, the book is also open. If sometimes you are unsure, it will take time to flip the pages and find the solution, but you have the 10 multiple choice and you have the 10 true false. Very quickly solve the ones which are very clear for you, and for the ones where you are a little doubtful, you can search in the book if you like. Ratio of crack tip to nominal stress is known as dash factor, stress concentration, stress intensity, critical stress, fracture toughness. So it's very obvious it is called the stress concentration factor, because the stress concentration is the maximum stress at the stress razor compared to the nominal stress, right? So this is a very obvious answer. For A very much larger than B, right? There is an elliptical crack where A is much larger than B. The crack becomes a sharp crack. Elliptical, penny-shaped, rectangular are not correct, yeah? Because this is an ellipse, and if A is very much large, the whole ellipse becomes roughly a flat line, right? So it becomes a sharp crack, you know that. Energy stored in the structure must overcome surface energy of the material to cause fracture, according to whose theory? Griffith, Inglis, Da Vinci, Galen, Cannon, Griffith. Right? Griffith has started all of this, that energy approach and so on. So this answer is rather obvious. The second part of question 1, which is the true-false. Crack tip plastic zone estimated from elastic solutions and von Mises yield criterion for mode 1 loading is larger for plane stress than for plane strain. You should know the answer, true or false. But again, if you forget, very quickly go into the book and find out. So this is true, that this is larger in the plane stress condition than in the plane strain condition, because when you use E is equal to E dash, then you divide by 1 minus nu square, right? And you reduce the value. Difference between Irwin and strip yield plastic zone corrections becomes significant for stresses larger than half the yield strength. Yes or no? It is false, right? You know the value, right? That for half the yield strength, yes, of course, but you have the graph of these two, comparative graph, and you know that the value is not exactly 0.5 here. The method of failure assessment diagram FAD is based on Inglis theory. What is your answer? You are right. It is based on, right, the other theory, not Inglis, so it is false. Effective stress intensity is divided by yield strength to make it non-dimensional. Yes or no? False. Right? Because stress intensity has other units, right? K has megapascal root meter and yield strength is only megapascal. So if you divide them, then it will not become non-dimensional. Similar quantity should be divided by similar units, right? A strip yield model is a typical example of the principle of superposition. Yes or no? Yes. Right, that is why they divide into small strips and then add up the whole solution. So this was the multiple choice and the true false part of quiz 3. Let us now move to the problem. 2a, a flat plate with a through thickness crack is subject to 100 megapascal tensile stress. The critical crack length for this plate is found to be 159 millimeter. What is the critical energy release rate GC of the material if its yield strength is 500 megapascal and its elastic modulus is 207 gigapascal? Any assumptions? So once again, I would encourage you to stop here, pause it, solve it yourself, and then go ahead with the solution if you like.